Hi folks, today we're revisiting axis intercepts on quadratic functions. So big ideas here for axis intercepts are if you want to find a y-intercept sub 0 for x. If you want to find an x-intercept sub 0 for y. And this is not specifically for quadratic functions, that's for any function. Now sometimes you can use the form of the function to help you out. So I've got stuff in two different forms here. I've got some trinomial stuff, and I've got also one that's in factored form. If I wanted to find the x-intercepts, I think the easiest one to do is probably C. But let's just do these in order. So the very first one, if I want to find a y-intercept, okay, I'll put in 0 for x. And some of you are probably already getting mad at me watching this. You're saying, hold on, that's in trinomial form. The y-intercept's just the number at the end. Absolutely. Okay? So really we don't need to do any work here to find the y-intercept on this if you recognize the form. If you don't, well, then you'll just go through putting in 0 for x. If we want to find the x-intercept, we're going to put 0 in for y. So we'll get 0 equals x squared minus 3x minus 4. Now, I would suggest that you pause the video for like 20 seconds and see if you can figure these out. And we're back. For me, I would definitely try and factor this. I think this will go a lot faster than quadratic formulaing. And if I'm unsuccessful with my factoring in about 30 seconds, then I'm going to give up and go to the quadratic formula. For me, under no circumstances will I complete the square. But maybe there are some of you out there who just love to complete the square. That's fantastic. All right, so once we get it factored, we know that the x-intercepts are going to be at 4 and at -1, the numbers that zero out these brackets. Okay. They're points, too. Hey? They're the point 4, 0 and the point -1, 0. We actually have a lot to go on to generate this graph at this point. What we don't have is the vertex, but it didn't ask us for that. So you could have also used quadratic formula. You also could have alternately just written this in factored form instead of going through all that work and been able to just pick off that the x-intercepts are at 4 and -1. Okay. You can write them either as a point or just as x equals. Doesn't matter. Next one. So this one, again, is in trinomial form, and it's important that we recognize what form we're given these functions in. It's in trinomial form because there are 3 terms. All right, so if I recognize it in trinomial form, I know that the y-intercept, is just the last number at the end. And that's the same with linears, hey? In a linear function in the form mx plus b, the last number at the end is just the y-intercept. And now we're going to go and we're going to find the x-intercept. And again, in that last one, if you didn't recognize the form, you could just put 0 in for x. Okay, for the x-intercept, we put 0 in for y. Now I'm going to have to solve this. And you want to, well, I guess ideally you want to factor it, but you want to do the easiest kind of factoring first. And notice that this has a greatest common factor. So take it out. Now that we've got it in that form, it's pretty easy to factor. You're looking for numbers that multiply to -3 and add to -2. Those two numbers are -3 and +1. And that means that the x-intercepts are going to be at 3 and at -1. You could graph on your GDC to double check. You could also have just written this function in the form of factored form. Okay, because it's factorable, I can write it as 3 by x minus 3 by x plus 1. And when I look at that by inspection, I know where the x-intercepts are, I know it opens up, and I know it's kind of steep. Lastly, we're looking for the axis intercepts in this one. So I'll show you a fairly slick way to do it, and then we'll look at kind of a sadder but also valid technique. So I can find the y-intercept by subbing in 0 for x. And that's not bad. I can't just pick out a number because it's not in trinomial form. So I have to actually do a little bit of work. There we go, y equals 6. Great. If I want the x-intercept, it's important that I look at what kind of form it's in. It's in factored form already. So what numbers are going to zero out these brackets? 3 and negative 1. So the x-intercepts are at 3 and negative 1. Pretty slick because we recognized what form it's in and what that form is good for. Factored form is great for finding x-intercepts by inspection. Okay, let's do the wah-wah version of this. Another option would be to multiply it all out. So I would start by foiling out my brackets. I'd have x squared plus 1x minus 3x, so that's minus 2x minus 3. Okay, and then I'm going to multiply that negative 2 in, and I'll do it carefully. Oh my gosh, I could botch this so easily. All right, I got it in that form. Ooh, that's great. Now I know my y-intercept is 6. I'm not sure that was an easier way to find my y-intercept. Now that I've got it in this form, I can go and find my x-intercepts. So I'll go and set this all to equal 0. Now, maybe somebody at this point will head to quadratic formula. I'm going to try and factor it. So negative 2 will come out as a common factor. And then I'll get this. Okay, that's good. And then I can factor that. Let's see. It's going to be x adds to negative 2, multiplies to negative 3. Okay, now from this form, I can say that my x-intercepts are going to be 3 and negative 1. Nothing wrong with this. But it's kind of sad that we took it out of factored form over here. Okay? And then later on, we factored it. We pretty much undid and then redid the process of factorization. Because what we end up with down here is the same as what we started with up here. So again, there's nothing wrong with doing it this way, but making good use of the form that you're given is probably a good skill. So the book doesn't have any explicit practice on exactly this technique of looking at the form and picking out the axis intercepts, but we have done questions before that have asked us for all the axis intercepts, particularly on page 34, question 8, if you're looking for stuff to do. What I'm hoping, though, is that this all makes you think about axis intercepts and the fact that not all parabolas have x-intercepts. The ones that we did here happen to, but they don't all have to. So that brings us back to the role of the discriminant. Remember, the discriminant is just b squared minus 4ac. Okay. It's the part of the quadratic formula that is under the square root symbol. And it tells us the number of solutions in an equation. For a function, it tells us the number of x-intercepts. So if the discriminant's positive, we have 2 distinct x-intercepts, 2 different ones. If the discriminant is 0, you have 1 x-intercept, or one, sometimes called 1 repeated x-intercept, though it doesn't really look that way. What does that mean in terms of a visual? 1 repeated x-intercept means that the vertex is on the x-axis. That's the only way you can have only one x-intercept on a quadratic. And if the discriminant is negative, then you have no x-intercepts. Now this might look like more stuff to memorize, but it's really the same rules that we had for equations. If the discriminant was positive, there were 2 different answers. If the discriminant was 0, there's 1 answer. And if the discriminant was negative, there was no answers. X-intercepts and solutions to an equation in equal 0 form really mean pretty much the same thing. So this is, how many x-intercepts does this function have? I mean, we could go through all the trouble of graphing it, but the simplest way to do it would be to consider its discriminant. So the discriminant on this function is going to be negative 3 all squared minus 4 times a, which is 1, times c. In other words, it's 9 minus 28. And that's negative 19. Which of these cases do we have? We have a negative discriminant, which means there are no x-intercepts. Let's go to the graphing calculator to confirm that. So when I graph it, there you go. It opens upward and it's above the x-axis. It has no x-intercepts. And we call that a positive definite graph. It's always positive. I mentioned before that sometimes discriminant questions are tricky ones that they like to throw in here. So this is one that would make you think. And if you want, you might want to pause the video at this point and give this one a shot, or see if you can make a little headway on it. It's okay if you can't get it all done, but think about what it's trying to tell you and what it is that you know and are trying to find out. So it says, for what values of m does y equals m x squared plus 3x plus m have exactly one x-intercept? Oh, IB, why do you give us all these extra variables? It's confusing, right? There are a lot of letters. But here's the key information. There's one x-intercept. As soon as they start telling about the number of x-intercepts or the number of solutions, this is a discriminant question. Here's what they have told us. They've told us we care about the discriminant, and the discriminant is 0. Okay, so the discriminant is b squared minus 4ac, and that's equal to 0. So b in this case is 3, so it's going to get squared, minus 4. A is m. Oh my gosh, and c is m as well. So right here, we've got an equation that's set up. And maybe we're not happy that it looks kind of confusing. It doesn't have any x's anymore. But we've subbed in the correct values. So let's just follow it through. 3 squared is 9. Minus 4m times m is m squared. All I have to do is solve this equation. So it's not a trinomial. I don't need to use quadratic formula. I think this would be a good case for either doing difference of squares, or probably better yet, just using the square root principle. Okay. Get that m squared term on its own. So we get m squared is 9 over 4, and then square root. Remember, when you square root in an equation, you need to consider the positive and the negative. So positive or negative 9 over 4 with a square root, or square root of 9 is just 3. That should be our answer. In other words, there's a possible value of 3 over 2 and negative 3 over 2. Now, you might or might not believe that that actually creates the situation that is given here. So let's try it on the GDC. I'm going to put in positive 3 over 2, which is 1.5. There it is. It's typed in with positive 3 over 2. Let's graph it. Ah, look, it really does have just one x-intercept. Let's change that to a negative 1.5. So I'm going to put a negative in for both of them, right? So I'm going to insert a negative. Let's see if it also gives us just one x-intercept. Yep, it's in a different place, but just a single x-intercept. In terms of practice, you could head to page 37 and do one, I don't know, maybe A, C, E. These are pretty quick ones. G and I. And you could also check out number 4. Okay. And when they say positive definite, that means no x-intercepts and opens up. In other words, there are no x-intercepts, I guess is the key feature there. And that one would be a challenge question. Okay, that brings us to the end of producing and describing quadratic functions from their equations. In the next section, we'll look at getting the equation from a graph. If you have any questions, please let me know, and take care, folks.